For decades, software engineering relied on strictly deterministic systems. You write a rule, and the computer executes it exactly. Today, we are attempting to build applications using large language models, engines that are inherently stochastic, capable of generating different outcomes every time they run. The initial industry response to this friction was to try and control the models directly. Teams spent months optimizing text instructions through prompt engineering, or expanding token limits to feed the model more data in a single context window. Over long task lifetimes, that approach breaks down. As an AI attempts to navigate a complex engineering ticket, the sheer volume of accumulating data crowds out the original instructions. The model suffers from context rot. It forgets key constraints or begins hallucinating software dependencies that do not exist. This friction point led the industry toward a new benchmark, the deployment of a million-line codebase with 0 manually written lines of code. This milestone proved that autonomous reliability is possible, but it requires a total shift in focus. When an agent makes a mistake, the solution is not to rewrite the prompt and ask the model to try harder. Instead, engineers must build a strict code-level constraint into the environment, ensuring the agent is mechanically incapable of making that specific mistake again. This equation defines modern AI architecture. An agent is a model plus a harness. The model provides the cognitive core, a probabilistic engine built for reasoning. The harness provides the context, tools, and execution logic required to translate that reasoning into tangible outcomes. Without a harness, an AI is trapped as a temporary chat interface. By engineering a harness, you transform it into a persistent, production-grade work engine capable of autonomous execution. The challenge is taking this isolated brain, providing hands to manipulate the environment, and eyes to observe results. The first primitive is the file system. Because complex tasks can't fit in a single context window, the harness uses it to offload outputs and store documentation. By combining this persistent workspace with version control, the agent gains long-term memory. It can track its own work history, branch out experimental implementations, and immediately inject knowledge gained from previous sessions into future tasks. The second primitive is the execution sandbox. To solve problems autonomously, the model needs to write and run actual code, querying the environment directly through a bash terminal. This execution occurs within an isolated, ephemeral environment. It allows the model to test its own hypotheses without the risk of deleting files or damaging the host operating system during the process. These primitives give the model agency. But giving a probabilistic engine the ability to execute code without strict architectural boundaries merely allows it to write broken code much faster. To restrict the agent's freedom, harnesses rely on a 3-layered architecture. It begins with Layer 1, constraint harnesses. These act as feed-forward controls. By mechanically enforcing rules like strict dependency directions, the harness narrows the agent's solution space before generation starts. To avoid context rot, modern harnesses utilize progressive disclosure. Instead of a massive instruction file, a tiny root file directs it to a highly specific, localized directory containing only the necessary execution plans. Because the model will eventually make a mistake, Layer 2 introduces corrective controls. Deterministic computational sensors, like unit tests and type checkers, run in milliseconds, catching errors and returning structured signals to the agent. This relies on a pattern called linter as prompt. Rather than merely flagging an error code, the harness translates that violation into a precise, actionable instruction. It tells the agent exactly why a service layer cannot import from a UI layer and provides the documentation to fix it. A critical security rule for this layer is disabling all suppression mechanisms. The harness prevents the agent from writing ignore error flags, forcing the AI to resolve the underlying technical debt instead of hiding it. Together, these two layers shift the burden of correctness. The outcome no longer relies on the LLM generating a lucky guess, but on the harness deterministically enforcing the rules of the environment. The final defense is Layer 3, enforcement quality gates. These are specialized barriers built into the continuous integration pipeline to prevent faulty AI code from ever reaching the main codebase. These gates are designed to catch semantic drift. This occurs when an agent writes code that is technically valid and passes all unit tests, but deviates completely from the original intent of the product specification. To detect this, the harness deploys specialized verifier agents. They analyze the implementation against a persistent contract, performing semantic checks to guarantee the new code integrates cleanly with existing architectural boundaries. This flowchart details the four-step agent loop: request composition, model decision, tool execution, and feedback integration. A variant is the Ralph loop. If a model prematurely finishes, the harness re-injects the prompt, bouncing off a locked gate until deterministic sensors confirm the tests are green. This table displays the metrics required to evaluate these systems. Because agents produce long trajectories of decisions, standard single-output LLM benchmarks are useless. Engineers measure readiness scores using tracking metrics like PASIT-K, groundedness, and the percentage of AI-generated code that requires human rework. A strict reinjection loop, measured by trajectory metrics, evaluates the system on its ability to autonomously resolve complex engineering tickets from start to finish, rather than its ability to write convincing chat responses. At the center of AI engineering lies a difficult paradox. Business operations, like tax reporting, payroll, and compliance, demand perfect determinism. Generative AI is inherently unpredictable. This matrix compares the regulatory reality of the two models. Under frameworks like GDPR, purely probabilistic systems carry massive audit risks. If an algorithm makes a consequential decision, auditors require a reconstructible trail of exact code paths, something statistical likelihoods cannot consistently provide. The architectural solution to this paradox is the hybrid control plane. The control plane uses rigid, deterministic workflow engines for routing and stability. It executes the high-volume, standard paths mechanically, invoking expensive, probabilistic AI models strictly for ambiguous edge cases that require actual pattern recognition. Achieving reliability at scale introduces heavy trade-offs. Ephemeral sandboxes and parallel verifier agents require massive computational resources, and the harness itself is a complex codebase that demands constant maintenance to prevent it from decaying. But the trajectory is very clear. The future of modern software development relies on orchestrating these complex mechanisms. The primary skill of a developer is shifting toward auditing the environment and encoding tribal knowledge into structural, versioned artifacts. The operating mandate for the engineer of the future is simple: humans steer, agents execute.